Hey, it's great to see you all. Good morning. And I'm glad you got to join us here rather than getting the recording. So I'm sorry, should I have shut up yet, Mark? Or are we okay?
No. Please,
Okay.
go right ahead.
Okay, I'm going to go. He can't stop me, right? Yes, he can. He's in charge. But Mark is great. It's so good that you're taking this class, and I'm really happy that you're doing so. The climate ethics is so important. What professors is doing for you is so important. So at any rate, let me do just a little frame. You all know this, but you need to repeat it every time you get together. I really believe that. Think of two futures, one in which we use our knowledge about our scholarship about climate and energy and ethics efficiently, and one in which we pretend that Mark and I are evil liars. Okay? And what's the difference between those two futures? And the difference is if we use our knowledge efficiently, we get a larger economy. We get more jobs. We improve our health, we improve our security, and by the way, we're environmentally and ethically sound. But right now, the economy is in the same way as ethics. And this message is not getting out the way it really probably should. I'm going to show you one. Mark told me to talk about the long-term future. I'm stepping on his toes. I'm sorry, Mark. But
go right ahead.
So I served on a committee with Bill Nordhaus. Bill Nordhaus won the Nobel Prize in Economics, co-recipient in 2018, for building tools which show that we are hurting ourselves economically because we're not dealing with this. Okay. Employment, this is employment in electric generation in the US. I have worked for an oil company. Fossil fuels make some good jobs. To first approximation, anything except fossil fuels is better. If you want to make jobs with your money, you get away from fossil fuels. And the reason is, as far as I can tell, this is not my area, but as far as I can tell, a lot of the money in fossil fuels goes to control of the resource. The cheapest producers of oil in the world can send it for $5 a barrel. They're getting 50. $5 is paying for jobs for somebody somewhere. The other 45 is because they control the resource, not because people make the resource useful. It's economic rent. And so if you want to make jobs with your money, you get off fossil fuels. We breathe a lot of particles from burning things, and they make us sick. Heat stress is going to be a big deal. These are doctors' organizations. This is what they say. Most important action we can take to protect our health is to accelerate the inevitable transition to clean, renewable energy. Dave Tetley, who just retired as a Penn State professor, but before being a Penn State professor, he was a Penn State PhD, and between those two, he was a rear admiral in the Navy. He was on this group. Our military leaders say if you change the climate and you drive refugees, they cause national security issues. And if you want national security, you need actionable agreements on stabilizing climate change, right? And then, by the way, if we don't change our energy system, we're going to drive things to extinction. And this is your whole class, right? This is red is changing the climate on top. Red is suffering from the changing climate on the bottom. How can anyone sleep at night when they're part of the red on top and not part of the red on the bottom? And so Jimmy Carter and the Pope will get together and tell you that this is just wrong, right? So the picture is, right now, you're looking at ethics, but if you were looking at economy, it's in the same direction. That's really, really important. Now, that economy thing says, look, we're going to emit CO2 now. How much should we emit? And they say that's going to cause damages. And we're really worried about the damages over the next 30 years. And then the next 30 years, the damages are somewhat important. And after that, we don't care. Right? Because either economic growth is going to take care of everything. Let me get my pen on here. Economic growth will make the damages insignificant, or else we just don't care. This is the pure rate of time preference. I think you've gotten to this already, haven't you, Mark?
We're actually going to be dealing with that in a week and a half. Yeah.
Stay tuned. Okay.
Yeah.
The assumption is, and the economists don't say this is good. They say we've watched how you behave and this is what you do. which is right now, they have in their economic model the fact that it is more important to take care of me as an old fart today than it is to take care of you students when you're old in the future. That is in there. And that's why they only care about the damages fairly close, because long in the future, we just don't care about you. Now, how one possibly justifies that in an ethics class, you will get to, so don't worry. But even doing this, even saying we only care about the next 30 to 60 years of damages, we are hurting ourselves by not dealing with climate. If we said, let's worry about longer times, then we should be doing way more now to not change the climate. The urge to get rid of fossil fuel emissions, if we did not assume these things, we would do an immense amount. Okay, so let me show you this. So here is some graphs, and I can get you these slides in your recording anyway. So the first thing to remember is that through some interesting physics and some trade-offs and some other things, more or less, how much we warm the world is just how much CO2 we emit. And there's an exponential fall off balanced against change in sinks, and this is a fairly complicated thing. But it actually does turn out that more or less how much we warm the world is just how much CO2 we emit. And that makes things easy for you to remember. More CO2, more warming. Okay, and it really does almost, if there's actually some hints recently that as we make it warmer, it will warm even more. So this could be a little worse than this. It can't be any better than this, really. Okay. So it is also worth remembering, you will hear people now on one particular side of the political spectrum saying, hey, we didn't grow emissions anymore. Isn't this great? We solved the problem. No. Okay. So what we need, if we wanted to stabilize, if we keep increasing emissions, CO2 in the air keeps going up. If we stabilize emissions, CO2 in the air still keeps going up because we're still emitting. And the total amount we emit is what matters. So if we stabilize emissions up there, what happens to CO2 in the air? It keeps going up. The only way we can stabilize CO2 in the air is to drop emissions. And in the short term, it's sort of kind of 80% drop. In the long term, it's 100%. If we want to quit warming the world, we have to quit releasing CO2, or else we have to take it out of the air, but not releasing it is way easier, to be honest. Okay, so 2 points: more CO2 emitted, more warming. If we are not going to do that, we have to quit emitting. We can't just stay where we are. We actually have to get rid of CO2. Okay. Whenever we quit emitting, we will get more warming for a while before it stabilizes. So here we are in the year 2000 or just past it. This is what we're doing, different versions of how much CO2 did we emit. So the different colors are different amounts of CO2. And what happens is as we run into the future, it warms even after we quit emitting. It will warm for a while before it starts cooling off again. And the reason is, right now, there's this humongous ocean out there, and we're making the top of it warm. But then that heat is being mixed down into the deep ocean. And because the heat is leaving the top and going down, that keeps the top a little colder than it should be. And that keeps the air a little colder than it should be. So the air, we keep trying to warm the air with our CO2, that heat keeps getting dumped into the deep ocean, or that heat keeps melting ice. A tiny bit is warming the land. And so we actually have to melt the ice and warm the ocean before we see the total warmth that we have caused. So whenever we quit changing the atmosphere, nature will warm a little more after that. We haven't seen it all, and we are committing you when you're old and your kids and their kids to more warming than we cause. And it's that kind, it sort of kind of takes 1,000 years until you're totally done with that. So, because the ocean takes 1,000 years to mix. If there are any questions, please yell at me. I don't think I see a chat, so I'm not sure if you can type into the chat, but you can raise your hand and we'll try to keep an eye on you and see what happens. So
there's a chat function, so students can sort of, so they can answer. And then I can see if there's any hands, I'll let you know.
Okay. Oh, there it is. I see it now. It's under more. Okay. Thank you. Okay. So, so there we go. So go back here now. And then this is also worth remembering. Once we stabilize the atmosphere, once we quit warming, if we keep the temperature up, that doesn't mean that the problem is solved. It means we're not making the problem worse, but the problem is still there. So this happens to be one. I don't know if you've gotten to this yet, but most of our crops are grown near the temperature that they like. And if we make it hotter, they don't grow as well. So this is how the global temperature changes. And this is what happens to production of the things we eat. And in different places, corn in the US or rice in Asia or corn in Africa. And what you'll notice is by the time we warm it some, everything, this is loss of half of the yield is right there. Our crops are not happy, right? Now, when we stabilize the temperature, that does not mean that the crops get happy again. It means that they are not getting more unhappy, but you've lost your ability to grow stuff, and that lasts forever until the temperature comes down. So yeah, okay. Where does it eventually go? And this is detailed technical stuff, but I think you're smart people, you'll get this, okay? And if not, you'll send me an email or you'll talk about it with Mark and we'll figure it out, okay? So what happens to CO2 when we put it in the air? Right now, we're putting it in the air. Every time a wave breaks on the ocean, it's a white cap. And what is the white? It's bubbles of air taken into the ocean. And there's CO2 that we put up there in those bubbles, and some of it dissolves in the ocean. Every time the wave breaks, there's little spray droplets, and those release CO2 to the air. So there's always trading CO2 between the air and the water. When we raise some in the air, some of it goes into the water. For the next 100 years, most of what happens to our CO2 is either it stays in the air or it goes into the ocean. And it goes into the top. So if we, in the model down here, this is time, and this is 100 years. And this is, in this particular version, they put this much CO2 in the air, boom. And then they said, what happens to the concentration? So nature was down here, and we're about here. So what would happen if we raise it to here and then we stop? We're not raising it anymore. And what would happen, we're not releasing CO2. What would happen is a little of the CO2 that's in the air goes into the surface ocean. It's still high after 100 years. We started down here and it's way up here, but it's dropped a little because it's gone into the surface ocean when those waves break and take bubbles down. Now, once the air and the surface ocean are pretty balanced with each other, you have to wait for the surface ocean to dump the CO2 deeper. And as CO2 leaks out of the surface ocean going down by mixing in the ocean, then a little more goes out of the air into the surface ocean. Now, the ocean is mixing really well at top because of waves. The wind doesn't mix it deeper very much. And so this is a slower process. So the ocean is taking CO2 down, but now this is 1,000 years, not 100. So once the surface ocean catches up, you've dropped CO2 about that much. To drop it that much more takes another 1,000 years, not 100. Okay. So now what happens? You've mixed the CO2 all the way from the air through the whole ocean down to the bottom. In the sediment underneath, there are shells of critters. And a lot of those shells are calcium carbonate, and they will react with the CO2 and neutralize it to some extent. So what happens next is you have to wait for the ocean to dissolve the dead coral reefs and the shells in the seafloor. And as the ocean dissolves the dead coral reefs and the shells in the seafloor, it uses up some more of the CO2. So over 10,000 years, you use up some more by dissolving shells. And then eventually, you end up reacting with rocks on the surface, and that takes more than 100,000 years, and you get back to where you started. So what happens to our CO2 is it takes 100 years to drop it some, it takes 1,000 years to drop it more, it takes 10,000 years to drop it more, and it takes 100,000 years to get rid of it. All right? Very crudely, that's the picture. Okay. Now, this is the really, really, really long-term thing. This is what eventually gets us out of this. This happens to be our colleague Jim Casting here at Penn State figured this out when he was a grad student. This is fantastic, okay? So what happens, this is supposed to be a volcano with big blobs of melted rock coming up, and the volcano spits out CO2 and calcium carbonate. And then a whole lot of chemistry happens that makes shells that go down subduction zone. That's the complicated version. Here's the simple version, okay? The volcano spits out rock and CO2. They come out, there's rock and there's CO2. The CO2 and the rock do chemistry, and that eventually makes shells that geology melts to feed the volcano. And the geology doesn't care whether the air is a little warmer or a little colder, but the chemistry does. If you've had a chem lab in your life, there's either a Bunsen burner or there's a hot plate in the chem lab. And why is there a Bunsen burner or a hot plate? Because you have to get the lab done before the period ends, and you have to make it go faster. And when you make it hotter, it goes faster. So this is true. So when it gets hot, what happens? The chemistry takes the CO2 out of the air and makes shells. When it's cold, the chemistry doesn't take the CO2. The volcano puts more up and it gets warmer. So because CO2 makes it warmer, this is a thermostat. This sets the temperature to wherever the geology and the life likes it to be. But the volcanoes are slow. We're putting out 100 times more CO2 than all the volcanoes on Earth. And so the volcanoes are really, really slow. So, and that means the rock weathering is really, really slow. We put up CO2. It's like a little more volcano. Nature will take it away in 100,000 years. Nature's going to forget about you in or a few 100,000, right? But it will last that long. There is another one that this one is a little more complicated, but I'll do it very briefly. Plants take water and CO2 and the sun's energy, and they make plant, right? So what is a plant? It's just CO2 and water plus the sun's energy and oxygen released. Then animals, bacteria, fungi, forest fires, everything else. Plants don't generally hang around. They get burned or respired to release the CO2 and the H2O and the energy. So there's this life cycle of CO2 goes into plants, plants get respired or burned or eaten or something, and they release the CO2. A little bit of plant gets buried for a while in the mud without getting burned, and it remains with its CO2. And we call that fossil fuel. If we make it hotter, there's less oxygen in the water. If you heat a Coke, it drives off the fizz. If you heat the water, it drives off the oxygen. That makes it more likely that the plant gets buried without being burned. So when it's really hot, nature takes plants and buries them to make fossil fuel rather than releasing their CO2. What we're doing is we're burning fossil fuels 1,000,000 times faster than nature saved them. Right? Just 1,000,000. And so we're taking all of that stored plant and releasing the CO2 and spitting it back out. But some of our fossil fuels were made in really hot times when there wasn't much oxygen in the water, dead zones, right? Dead zones are good for burying gunk in the mud. Okay, so now a little aside here, see if we're doing okay. I do history of climate. I teach a whole course in the history of climate. If you took the whole course, you would at the end say, well, look, CO2 has been the single biggest control on climate in Earth's history. It's the biggest thing. It's a big control knob. Nature has changed CO2. We're changing CO2 faster. The only thing really in Earth's history that is both bigger and faster than what we're doing is a meteorite that killed the dinosaurs. And otherwise, we're almost as big as the biggest things and faster than virtually everything. So I'm going to show you for just a moment, this is a history of nature change. This is 65 million years ago. So the meteorite kills the dinosaurs right here. This is a history of nature changing the thermostat a little bit. And I want to take you to this little blip right here. Nature released about as much CO2 as we might, a lot slower than we will, okay? But here, this is a wonderful picture from the ocean drilling project. And these are pictures of mud brought up from the seafloor. And this one, when it had been drilled, would have been like that in the seafloor. Here's a picture of similar cores from the seafloor. This mud is full of little tiny shells of creatures that lived 55 million, 56 million years ago. They're carbonate. They are what gets dissolved in that 10,000 year part of taking our CO2 out. And this is where nature dissolved the shells. So that is red, not white, because the white shells are dissolved and you can see the red dust that's behind it. Nature released a lot of CO2 56 million years ago, and it dissolved the shells over 10,000 years and longer in the same way that nature will dissolve the shells with our CO2 in the future. And this is one of these things we can check. Do we really think we understand what we're doing? Of course we do. It's right. Okay, and we know this. We've checked it.
It's amazing to see it so clearly.
Isn't it? That's it. That's where the CO2 went, was dissolving the shells. It's wonderful. Here's a whole bunch of cores with the same thing. And there's no, Tim Brailauer here at Penn State has worked on these sediments, and there's no carbonate in there. It's all gone. Wow. Now, what happened? Nature released a lot of CO2 and it got hot. And then over long times, nature released some more CO2 because the soils were losing their carbon, and it stayed hot. And eventually you dissolved the shells, and then you dissolved the volcanic rocks, and then you got rid of it. And it only took 100,000 years or 200,000 years. And it was hot until then. And the CO2 apparently came from this giant volcanic outpouring when Iceland started. And it made these big these are basalt flows. And there was this giant volcanic outpouring, but it took 10,000 years, right? And so what happened then is 10,000 years of volcanoes, and then the soils lost their carbon, and then it took 100, 200,000 years to get rid of it. And while it was hot, what happened? And we had huge warming in the ocean, things migrated, things went extinct. We had dead zones. We dissolved the seafloor carbonate shells. We had stress on living things from acid and from heat. We start producing poisonous gases a little bit in a few places. We drive things to extinction. On land, what happened? If you were a big warm-blooded animal, you got dwarfed because it was really hard to be a big warm-blooded animal. Insect damage to leaves, the soils lose fertility, things go extinct or they migrate. Yeah, you release a lot of CO2, it's a big deal. And nature proves that. Now, okay, if anything, the temperature changed more than our models, not less. If anything, the temperature changed more than our models, not less. The impacts on living things were larger than we expect, not smaller. this is important. There's a little debunking here, okay? You know that we've always had natural forest fires. And when it's really dry and there's a whole bunch of things that can burn, we don't like people going out with illegal fireworks and setting fires. Because fires have always burned, we should worry about humans burning things. You know that people have always died. And so we worry about somebody walking by with a few bombs and explosives and poisons and what have you, right? We have a homicide division at the police department because we know that people have always died. People have always died, so we should worry about humans killing people. Fires have always burned, so we should worry about humans setting fire. I walked into the senator's office and the senator said, climate has always changed, so we should not worry about humans changing climate. I have had more people tell me this. Climate has always changed, so we should not worry about humans changing climate. Can you possibly imagine someone saying people have always died, so we don't have to worry about murder? Can you possibly imagine any person saying fires have always burned, so we don't have to worry about arson? We have a government that has got a whole lot of people in it right now who say climate has always changed, so we should not worry about humans changing climate. I don't know where to go with this, right? Climate has always changed, so climate is changeable, it's proved. Climate has always affected living things, so climate change is important. Climate has changed for a lot of reasons, but especially CO2, so our CO2 is especially important. And the truth is, if you took our class, the more you know about the history of climate change, the more worried you get about the future of climate change. And the idea that this argument is floating around out there is just blithering idiocy. I'm sorry, right? So it's very clear that this is the case, right? That we understand what happens. Our CO2 will last a long time. This comes from extensive understanding. We check it against history. It works. This is accurate. But I'm going to do now one more, and then I'll try to shut up and we'll do a little discussion. Because another one that the senator did, I was in a hearing and this was very uncomfortable, but the senator was spouting nonsense. And so, which is, there are a number of people in our government who say, well, this 100,000 years is a lie, it's 4 years, right? And what they've done is this. Right, so here we go. This is the Keeling curve. This is the history of CO2. It's not quite up to modern, but this will do. This is measured in the atmosphere in Hawaii. And what do you see? First of all, is there's a seasonal cycle. Each of these is a year. Every spring, the leaves grow. And they take CO2 and they make leaves. And then every fall, the leaves die. And then they rot or they burn and the CO2 goes back in the air. And what you see then is spring, fall, spring, fall, spring, fall. And then you see the rise in CO2 because we're burning fossil fuels. Well, what that people will try to do to you, which is completely wrong, is they'll say, look, this is going down really fast. If that kept going down, you'd run out of CO2 in 10 years or something. So CO2 can't stay in the air long, so we don't have to worry about our CO2. This is true. The senator sat there in a hearing and said this, okay?
Oh, no.
Oh, no. It's really scary, okay? But what it is, technically, if this were a CO2 molecule right here, I just grabbed him, George, right? George, the CO2 molecule. If you were to watch George and say, how long are you in the air? It isn't terribly long because George goes into a leaf. Or, wait, hang on. George just left the air and came back. Okay. George goes into a leaf in the spring. George comes out of a leaf in the fall. And the senator is saying, well, CO2 only stays in the air 4 years because it goes in the leaf. But so the senator says we have spring and we don't have fall. Right? This is true. So what we do, this is how CO2 goes if we put it in the air and what happens to it. So this is now, if we put a lot of CO2 in the air, it drops pretty fast, and then it drops slower, and it's back to this is 1 million years. Okay, so most of it goes out in 100,000 years. If we don't put so much CO2 in the air, it drops out a lot faster. But it's still sort of 500,000 years before you're completely back to where you were. This is a log scale, but it's the same story. If you do temperature, when we quit adding some, it warms a little more, and then it drops off. This is 1 million years still. It's actually back all the way to where we started. And then this is sea level. If you take an ice cube, you drop it in your iced tea, it takes a while to melt. The iced tea is warmer than the freezer, it's melting, but it takes a while to melt. If you make it hot, it takes a while to melt the ice. And so this is what happens to sea level above present. If we warm it a lot, it starts rising. It rises for a while, it gets really high, and then it takes 500,000 years to regrow the ice sheets. And you've raised sea level for 500,000 years. Okay? If we melt all the ice, if we burn all the CO2, we commit to melting all the ice. What does that do? It puts underwater where 1/3 of the world's population now lives. It puts underwater where 1/6 of the world's crops are. And it takes a while to go under, but we commit to doing that in the same way that dropping that ice cube in the glass of tea committed to melting it. And so even if it doesn't melt in your lifetime, once it gets hot, you're committed to melting it. The heat stays, the CO2 stays, it's long term. And you're talking about telling somebody in the future, far enough away that the economists are not worried, that if you're 1/3 of the world's population, we're going to kick you out of your house. Right? And I could go on, but I think I'm just going to shut up at that point. And so the biggest picture, yes, the science is good. Yes, the science is solid. Yes, we have checked it against the past and it works. Once we put a lot of CO2 up, it will get hot. It will stay hot for a long time. It will change the climate in ways that impact people and crops and other things for a long time. It will melt ice and it will keep warming for a while, and the changes will be really big.